So today we're talking about Coulombs Law, and I figured since I'm a physics major, I should probably put some videos with physics in them. I seem to have more of the mathematics videos right now, but I hope to bring both to the table in various subjects. So this is actually the first video in my playlist. Is going to be electromagnetism, which is my favorite subject in physics. So we're talking about Coulombs Law. Basically, what it says is it describes the force between two charges, positive or negative, and basically what it's saying is the force is, let's see, where is there? Force is proportional to the product of the two charges, Q1 and Q2, and inversely proportional to the distance between them, or big R squared. Now, when anything's proportional to something else, you can set it equal to that something else with a constant of proportionality k. Now, what's usually done is this distance between them is, since this force acts in a radial manner, this bottom term is usually 4 pi r squared, because that's the well, it acts over a surface of a sphere, and then this k turns out to be 1 over epsilon 0. That's just the proportionality constant that was determined, and they just bring it into the denominator, and that's 1 over 4 pi epsilon 0. That's the constant term. Now, epsilon 0 is called the permittivity of free space, and what that means is a permittivity is a measure of how well an electric field can develop inside a medium. And free space, or vacuum, is the medium in this case, and epsilon 0 describes how well that electric field can form inside free space. Now later on you get into material space, where each material has a different way that electric fields can form inside of them, and therefore epsilon 0 is not the correct term. You actually have epsilon r, and we'll get into that later. Basically, it's just a measure of how well electric fields can form in free space, is epsilon 0. So this is Coulomb's law right here. I'm going to put a little box over it, and I should probably give the value of epsilon. Epsilon 0 is found to be 8.854 times 10 to the negative 12th farads per meter. So I'm just gonna do one of these things, farads per meter, and farads being the unit of capacitance. Units aren't terribly important. This constant of proportionalities usually have strange units because it has to equal force, the units on the right hand side. So okay, so we have this expression, and we're just going to develop it a little further here. This r squared is the distance between the two charges. So I drew a little something in paint. I hope that's coming in okay. Maybe I'll move it to like right here, so it's more in the middle. Okay, so alright, so this point right here is our origin. In fact, I'm gonna write that. Origin. That's the point right here of like a Cartesian coordinate system. And here's charge 1, charge 2, described with position vectors r1 and r2. Yes, they should have a little arrow on top of them, but hey, this is paint, and not very good in paint. But So we got this going on, and remember we said the big R, or R12, is the vector between the two charges. So the way to obtain that in vector form is, well, we're going to say that big R, and it's a vector, so I made it bold, R12 equals R2 minus R1, and that will give you this vector right here. Yeah, a little bit of vector analysis. So let's see here. Next in my note. So, alright. So force is typically a vector quantity. In fact, it is a vector quantity. So, and what we have here is a scalar. There's no sort of direction implied in this expression right here. So we want to write this as a vector. Oh, oops, as a vector. No, not D, F. And I'm going to write this as a vector. So we have to use our vector notation. It has to be in the direction of R, of big R. So it has to be in the direction. So we're going to call it A sub R 1, oops, not superscript, 1, 2. Because it's in the direction of R12 from this picture right here. So R1 A sub R12 though, what's that? That's going to be vector R over the magnitude. Where's my little magnitude? There it is. Over, oops, nice bar. Over the vector R magnitude. And we can rewrite that as a lot of times we'll just rewrite this as just R like this, but I'm going to keep it into magnitude form like that, just so it's consistent. So this is equal to R2 minus R1, and then divided by the magnitude of R2 minus R1. So that's our A sub R12. Now if we plug this into here, well, first we can replace this R right here by R2 minus R1, and then our A sub R can be replaced with this, like that. And then these denominators in the bottom are going to multiply together and give you a cubed, and that's going to go in the numerator. And here we go. This is the vector form of Coulombs Law. It can be written like this, or it can be written as we had before, where we just replace R2, R1 with R1, 2. So like that. Or it can be written like this. They're all equivalent. I don't want that F in there. All equivalent ways to write the same thing. So, as hopefully everyone knows, you have if you have two positive charges, they're going to repel each other. If you have opposite charges, they're going to attract each other. You got two negative charges, they're going to repel each other. So let's see what's next in my notes. Turn this page here. If we have more than two charges, because this equation just represents two charges, Q1, Q2. That's it. What if we have, I don't know, 7 charges, 20 charges? How do you describe that sort of behavior? And the thing is you have to pick a point of reference. A point of reference where you pick one charge you want to examine, and you find the force on that charge from all the other charges. and that force is going to be the quote-unquote superposition of all the forces from all the other charges. So basically, it's going to be F equals, I'm going to just copy this and replace some subscripts here. The charge we're interested in, we're just going to call it Q. So then this is going to be Q1, this is going to just be R, that's going to be R1, that'll be R, and then so that's the first term, and then you have to add up this from the second charge. It's just taking the force from each charge, U2 plus, then we're going 3 from the third charge in the array that we have going on here, 3, and then, you know, plus dot 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 for however many charges you have. And this could be summed up conveniently into a closed form as, scroll down, Q 4 pi, let me just copy it, epsilon 0 times the summation from k equals 1 to n of, well, Q sub k r minus r sub k, and then divided by the magnitude of those vectors. So if you go through this summation formula, you'll get this expression. You know, when k equals 1, you just plug it in, you get this one. K equals 2, you get this one. And they're added together. This is the principle of superposition. You just take into account all the forces from all the charges at all the different distances from a certain charge that you're examining. So that's basically it. Not too much. I mean, it looks, you know, kind of crazy. The people who aren't really so used to working with this, you know, somebody walked behind you in the room and saw this, they'd be like, you know, what the hell is that? It looks crazy. What kind of crazy, wacky math do you do it? No, it's not that bad. It's just a summation. So, it looks more complicated than it is. Alright. So, our last, you know, subject to this video. How long is this video going on right now? Okay, so our last subject is, I want to do an example, but it's getting a little bit too long. So, I'm going to do examples in other videos, just so I don't have like an hour-long video. So this video is more of just like the theoretical stuff. The last subject is electric fields and or electric field intensity, which is denoted as vector E. It's a vector field. The electric field intensity or electric field strength, E, is the force that a unit positive charge experiences when placed in an electric field. Now it's a unit positive charge just by convention. That's just how it is. I guess they didn't want to deal with the negative side in the definition. So it's basically well, let's take our expression up here for force. It's basically the electric force divided by some test charge. And it's you basically take the limit of this value as the test charge tends to 0. You know, you got a test charge, you put a test charge in an electric field and it experiences some force. So actually technically I should be writing it like this. But, you know, they write it like this for simplicity. You basically put a test charge in a field, it experiences some force. And then the charge on that test charge, just make it smaller and smaller by somehow. This is the thought experiment. And the value approaches a limiting value, and that limiting value is the electric field intensity. And the mathematical expression for that is simply just the same as the force, except you divide out one of the q's, because that was our test charge. So that's what it is. And now in this case, since we have one charge, our vector is going to well, hold on a second. Let me look at my notes. Looking at the notes. Okay, so it's like it works the same way as electric force. Is what I'm trying to say. Remember before we had we had multiple charges, and we just summed up all of the contributing forces from all the charges everywhere, and that gave us this expression. Now, similarly, we can find the electric field due to multiple charges, because every charge gives off an electric field. So if we have multiple charges, there's going to be some interaction between electric fields, and we need to take that into account. So what I was trying to say before is that these vectors are pretty much, they're the same type of vector. You have to take into the same type as we worked up here. You have to take into account the distances from each charge to the charge you're interested in, and find the electric field on that charge from the other charges. So each this might sound like a lot, but it's basically every charge puts out an electric field, and if you have multiple charges in one area, there's going to be some sort of superposition of that electric field, and it's described by this. And you could sum this up in a whole summation formula in a similar fashion, and it's going to be E equals 1 over 4 pi epsilon 0. Nope, in the denominator. Then we get the summation. K equals 1 to n of q sub k, and then we have our vectors, which we had last time, r sub k, and then so this is working. Where's my little magnitude sign up here? Magnitude r minus r sub k. Oh, not sub l, sub k. And that's it. That's this is the same logic as the force. It's superposition, and these expressions actually look almost identical. But they should, because of this definition. So that pretty much wraps it up for this video. Sorry for that. For this video, I want to do some examples, but I will have to do that in another video, so this doesn't get crazy long. Thanks for watching.